Is anybody here who was not at the first 3 lectures? Probably not, right? I thought that there would be some extra people, and so I prepared something which started again with an introduction that you actually, some of the slides you've actually seen already. So, but on the other hand, I guess I personally feel that it's not that bad when I hear things twice, maybe even 3 times. I find it kind of useful. So maybe I'll go through quickly, just remind you a couple of the things I said before, but maybe not the really introductory slides. So yesterday I was talking about active nematics, and in particular I told you about, at least I give you one example of an instability that occurs in active nematic, that we call it spontaneous flow instability, by which the system, a layer on the nematic crystal, turns into goes into a state that has especially inhomogeneous deformations of the other parameter of the director field and a non-zero flow velocity in the absence of any externally applied forces or fields. And what I want to do today is discuss more in general some of the other instabilities that happen in exactly nematic, and in particular these kind of flows that I showed you yesterday as seen in experiments, and tell you how we try to describe this behavior, which looks a lot like fluid turbulence, although in a system that is effectively at almost 0 Reynolds number. And we're trying to describe this behavior in terms of the dynamics of topological defects, particularly discriminations in nematic crystals. So I will probably skip some of the slides I had at the beginning. They were just to introduce people again to what active matter actually is. But I just wanted to point out that today I will actually talk. For the first few lectures, I told you things that some were done by me and my students and collaborators, some were done by others, and I never really bothered too much actually telling you who did what or giving proper credits. But today I just want to highlight that the work that I will talk about on defects particularly has actually mostly been done by a former student of Syracuse, who is now moving on to Leiden. A couple of current students, Schumacher and Misha, was done with Mark Bowick and with the former postdoc Rasmus Knepnik, who is now at Dundee in the UK. Is this a, well, I guess this could be a pointer, right, also? Yes. Okay. So it's not big, but that's okay.
There's another point adjacent to the board.
Well, this is it. Oh, I see. Right there. Okay. That's what fighters have. So, okay, well, nematic crystals, again, systems of liquids composed of rods that, as you increase the density or lower the temperature, but in the active systems I'm interested in, this happens as you increase the density. They order in states with orientational order, states that are, however, head-tail symmetric, they're still liquids, but up is the same as down. And so the direction of order, although we denote it by this unit vector we call the director n, this unit vector is really not a true vector. Typically it has two-headed vector because the state is symmetric when I turn n into minus n. And okay, so that's the symmetry. And active nematics are liquids of rod-like, again, particles or units, but these particles or units are active in the sense that they internally generate forces of motion, and these forces act on the surrounding fluid and generate the kind of active stresses we discussed yesterday. And these are actually the examples I gave you yesterday, these these suspension of microtubule bundles. And this is the E. coli swimming in a nematic liquid crystals. I will not go through it again. I might just show you the movie one more time of the experiments of the Brandeis group of the dense suspension microtubule bundles, just to stress again that what's happening is this spontaneous swirling motion and folding, if you like, of these regions of order structure. And then you see that there's the spontaneous generations of topological defects or disclinations here. These are highlighted by these arrows. That's a -1F defects. We'll see that better in a minute. There was a plus, that's for like a +1F defects that looks like a comet with a tail. And these defects move around and sort of steer the system. And this looks a lot, being referred to as low Reynolds number of turbulence. So that's the kind of dynamics you'd like to understand. I want to show you two more examples that I did not show you yesterday. I actually showed you this image. This is a single fibroblast which behaves like an active particle with nematic symmetry because it just keeps moving back and forth. Now the time scales here are very different from the ones in the suspension of microtubule bundles. The microtubule bundles are typical velocities that you see there of the order of 10 microns per second. Here, they're more like microns per hour, so cells are much, much slower. But the dynamics is, and the scales are also different, scales are also larger than the microtubule bundles, but the dynamics is actually somewhat similar. And although it's not quite as obvious, but if you look at this image, it doesn't seem to come out all that well here, but you should be able to also see here sort of regions of nematic order and topological defects that are generated and move around in the system. I don't know why the quality here is so low, so you can't quite see. But that's another example of an active nematic. Now, what is different about this active nematic, and this will become relevant in a minute, as compared to the microtubule suspension, is that yesterday we discussed these active stresses. I pointed out how this active particle can exert stresses that are either contractile or extensile. The microtubule bundles, the kinesing sort of shifts the filament in and out of the bundle, and so the bundle itself is an active particle that pushes out of the surrounding fluid or exerts extensile stresses. Cells, like the fibroblasts, these are on a substrate, this is also a two-dimensional image, they actually tend to pull in, they exert contractile stresses on the surrounding medium. And so this is an active nematic which is contractile, and we will see in a minute how that affects the dynamics, and in particular the dynamics of the defects. This is actually not a living system. This is a layer, a single layer of rods. I think these were I think these were copper rods, about 5 millimeters in length, in a dish. This is 2,820 of them. The dish is vibrated vertically at a fairly low frequency. And this vibration, of course, you could ask, well, these particles are not really self-propelled, right? Because it's actually the vibration that propels them. But what is important here is that because of when they bounce up and down, they tend to fall at all kinds of random angles, and though each one of them acquires a self-propulsion velocity, which is different for each one of them. And if you like, what I like to think as the fundamental property of this active system is indeed that each one of the particles is propelled in a different way as compared to the others. And so this this layer of vibrated rods behaves very much like a collection of self-propelled particles, and it shows the dynamics of an active nematic. Okay, again, local order and defects. And unfortunately, these images don't come out very well here, so you can't really see. But if you want to look at them on my computer later, I can show you that you can actually see the defects just like you saw in the microtubule suspension. Okay, so we want to describe these dynamics. Again, nematic in principle, you have a homogeneous order state, and everybody is pointing around one direction. That's the direction of the director. and the order state has some value for the order parameter, which I picked to be 1 in this case. But even in equilibrium, nematic liquid crystals, when, for instance, you generate them by quenching down from the disorder state from higher to lower temperature, you never get a perfectly ordered liquid crystal. You actually get regions of order separated by topological defects. And the lowest energy defects in nematic liquid crystals are called disclinations. They're characterized by something called a charge or a strength, which essentially is, they are especially inhomogeneous, so the defect is especially inhomogeneous configuration of the director. Here's an example of one. And the way you characterize the defect is you start over here, say the director points this way, and then you look at how much you have to rotate the director as you go 360 degrees around the defect to go back to the original state. And in this case, you will see that you have to, if you go around clockwise, your director will rotate clockwise of 180 degrees. So the charge of strength and the defect is the ratio of the angle by which the director rotates to the angle of rotation of your path. So it's 180 to 360, and so is 1F in this case. For this other special inhomogeneous configuration of the director, if you go around again clockwise, the director will actually rotate in the opposite direction, so it rotates of minus 180 degrees, and so the strength of this defect is minus 1F. Of course, in a nematic you can also have higher strength defects, which are then the same as you have in a ferromagnetic system, but these are the lowest order defects. And of course, the system is well ordered away from the defects, so you can say in this legion state, the magnitude of the order parameter is still 1, but at the core of the defect, this little region over here, the order parameter goes to 0, and the core of the defect is essentially a normal region. So again, defects, spatially inhomogeneous configuration of the director, but very characteristic one that have a topology which is actually determined essentially by the type of broken symmetry you have in your system. Now, in equilibrium, again, when you quench your system, say from high to low temperature, getting to a nematic state, defects are always generated in pairs of opposite sign, because the total topological charge, which is the sum of the charge of all the defects, has to be conserved in a system. So if you have a planar system in 2 dimensions, it was perfectly ordered, there are no defects, the total topological charge is 0. If you start at high temperature and generate the order state by quenching, well, you start with a 0 topological charge, you must end up with 0, but defects are generated, so they're generated in pairs, as many plus 1F as minus 1F. Defects also sort of really do behave like particles in the sense that opposite sign defects attract, same sign defect repel, and the interaction in 2 dimensions is logarithmic. So if you were to wait a very long time in equilibrium, the defects will tend to annihilate, and you can actually reach a defect-free state. And defects in nematic crystals are very real. If you put the nematic under cross polarizers, you will see something that looks like this actually. And the defects corresponds to this point where these dark and light brushes that correspond to different orientation of the director in all the regions meet. And you can actually, by studying, so whether the number of brushes that meet tells you about the charge of the defect, whether there are half integer or integer defects here. So they're very real, and they're there in equilibrium systems as well. Now, I said that the topology of the defect is controlled by the symmetry of the order state. And so again, in nematic, you have these plus or minus 1F discriminations, which are the lowest energy defects in equilibrium. And this type of structures, as we saw already, but here's another example, are seen in living systems, in active systems. So this is now, we see quite clearly that this is now a -1F discriminations in a collection of melanocytes, other cells that are nematic in symmetry because they just go back and forth. This is a +1F discrimination in a film of a bacterium called Myxobacteria. Myxobacteria is a rod-like bacteria that does not swim in a fluid but glides on a substrate, and also a tendency to goes back and forth, actually retraces itself, and forms lens structures which are also nematic in nature. Now, if you had a system that has polar symmetry, to be E. coli, or actually the example here are individual microtubules driven by kinesin. Remember, the microtubule bundles I showed you before are bundles of microtubules where, say, half of the microtubules are pointing one way, half are pointing the other way. And so the bundle itself is an active unit which is nematic in nature. The individual microtubules are actually polar. They have they are different at the two ends. They polymerize at one end, depolymerize at the other. And kinesin always walks towards the so-called placenta microtubules. So these are sort of polar particles. And so if you have individual microtubules and kinesin in a suspension, you see that the motor proteins drive the formation of structures that have this type of topology. These are called asters. And indeed, you could think now that they actually are topological defects of charge +1 of a field with ferromagnetic or polar symmetry. Another +1 defects that is possible in this kind of system are vortex-type structures, which are also actually have been seen in suspensions of microtubules and kinesin. In fact, actually, this type of images, which were obtained a long time ago, this work on this started back in 1999 and 2000, for instance, by the group of Stan Leibler, was at that time at Princeton. This type of motor-driven pattern formation in suspensions of microtubules is sort of actually what started the interest of physicists in the whole field of active matter. So, but the point here being is systems with different symmetry, polar versus nematic, the topology of the defects is different, and in some sense, that's one way that you can use to try to decide whether your system indeed has nematic or ferromagnetic symmetry is by looking at the type of defects that you see in your system. If you see disclinations, you know that this system has to be a nematic. It does not have polar symmetry. Okay, so how do we describe defects? I'm going to do it again at the continuum level, so I'm going to go back to my hydrodynamic model of active nematic that I introduced yesterday, to the equations I introduced yesterday, and show you what I can do with them to describe the defects. The only thing is that today I will actually write down equations for the full order parameter, the so-called alignment tensor. So again, the nematic order can be characterized by so you think of the molecule, each one of them, making an angle theta alpha with the x direction, or characterized by a unit vector and u sub alpha. And in order to pick up this kind of order that has nematic symmetry, you define the alignment tensor this way in 2 dimensions, or at the macroscopic level, equivalently in terms of the order parameter and the director. So S is the strength of the order, and this is the direction of order. And yesterday I kind of sketched hydrodynamic equations for the director, which are appropriate to describe the dynamics deep in the order state, where S is approximately constant everywhere. But if I want to think about defects, the defect is especially homogeneity in the director, but S, the order parameter magnitude, goes to 0 at the core of the defect. So in order to identify defects and follow their dynamics, it's actually useful to look at the dynamics of the full alignment tensor, and that's what I will do next. So I will rewrite the hydrodynamic equations as an equation for Q instead of an equation for N. But I've written it here in a sort of, I dropped a lot of terms, sort of in a simpler way than I did yesterday. So the dynamics of this Q, first of all, has a damping term. This is the gamma, is what in liquid crystals is called the rotational friction. Q is not a conserved quantity, and so the leading order it decays with a rate that is controlled by this rotational friction. There is a term here that describes the energy cost associated with creating spatial inhomogeneities in this order parameter Q, and K is an elastic constant, is a stiffness, is a Frank constant, assuming, again, I have assumed here that in 2 dimensions you only have band and splay deformation, and I've assumed that the energy cost for those are the same, which is not generally true in a real system. And then an important term is the coupling of orientation and flow, controlled by this parameter lambda that I discussed yesterday. V is the flow velocity, so I have a coupling to gradients of the flow velocity. There is an important time scale in these equations that I would like you to keep in mind, which is determined by this friction, which is essentially the time scale over which the local structure, local inhomogeneities in the order parameter can actually relax. This is the time I call tau p. Is determined essentially by the ratio of gamma to the stiffness. K divided by gamma actually has dimensions of diffusion coefficient, so if I multiply this by the square of the length, I get the relaxation time. And this length scale, which will come in later, I could imagine here the length scale. So if I have a spatial inhomogeneities on length scale L, it will relax with this time scale. That's one time scale to keep in mind. There is nothing about active systems in these equations. This is an equation for passive system. In principle, activity could come in this A in shifting the location of the isotropic nematic transition, but we're not going to worry about that today. Second equation I need is the Navier-Stokes equation for the flow velocity, which I've written here in sort of a schematic, simple way. The flow is determined by viscous stresses, it is the shear viscosity, gradient of pressures, which will actually drop out because I'm assuming the system to be incompressible, constant density, and stresses in the system. Stresses are elastic stresses arising from, again, spatial deformation of the direction of order, and I haven't even written down the expression for this quantity, which is complicated, and the active stresses I introduced yesterday. And in general, I have both active stresses proportional to Q. I actually also have active contribution to the pressure, because this stress also has a component which is isotropic. And actually, the reason I wrote this down is because I wanted to highlight here something that I said yesterday. Yesterday, I said that, so the active stresses arise from these force dipoles that the active units exert on the medium. And I pointed out that the sign of these parameters, alpha and alpha prime, tells you whether the stresses are contractile or extensile. Now, it's easy to understand this and also even to remember it if you actually think in terms of the isotropic component to the active stress, which is really a component of the pressure. Now, the pressure usually has this minus sign in front. So if alpha is positive, alpha prime, let's take it equal. If alpha prime is positive, this term is like a negative pressure. And so clearly this is a contractile system. It tends to pull in. If alpha is negative, this is a positive contribution to the pressure, and so it's an extensile system that pushes up. Okay, so if you think in terms of pressure, it's easy to understand the meaning of the sign of this alpha. There is a second important time scale in this equation, which I will call tau sub A, which is the ratio of shear viscosity to the strength of the active stress. And this essentially controls the rate at which these active stresses are injected in the system before they can be dissipated by viscous stresses. Okay? And it will be the interplay of these two time scales the relaxation time for the microstructures I introduced before, and this tau A, that will generate the interesting dynamics I'll show you in a minute. When did I start? When am I supposed to end?
In about 40 minutes.
Okay, just not. Okay, thank you. So, what can you do with these equations? Again, you can try to find some simple solutions, or you can look at the instabilities, and we talked about some instabilities yesterday, but yesterday we talked about the spontaneous flow instability in a confined system, in a field. Of course, the same instability also occurs in, say, in a planar system, which is with periodic boundary conditions and so on. And as I want to stress, to highlight, describe this instability a little bit more than I did yesterday. So we said yesterday the instability essentially is generated by the fact that you have this active stress here, and even if you don't apply any forces to the system, which means you might want to maintain a situation where the total stress is zero, the system can do that, can maintain zero total stress, by creating shear flows that will balance the formations of the order parameter. On the other hand, these shear flows that are generated may actually result in instabilities in the following way. So let's imagine a system which is ordered in the x direction. And let's look at spontaneous fluctuations which may take the form of a splay deformation, which I've tried to draw here. So we have a splay deformation of the director. The splay deformation of the director, according to this equation for the stress, will actually generate the shear flow. And the shear flow generated, if alpha is positive, if you're looking at a contractile system, will have the direction of these blue arrows. But that means that the shear flow that is generated actually tends to make the splay even larger. And so the system is unstable, so a contractile system is unstable to splay fluctuations. If you have a band fluctuation, a contractile system will generate a shear flow with points in the direction opposite to my arrows, and so the contractile system will be stable to splay fluctuation. But an extensile system, alpha negative, will generate a shear flow in the direction of my arrows, and that shear flow tends to actually enhance the band fluctuation. So an extensile system is unstable to band fluctuations. And now if you think back of the movie of the microtubule bundles, what you saw there was a lot of band fluctuations, right? This movie where the structure was bending and moving around, flowing around all the time. There was lots of band fluctuations in the system. Indeed, that was an extensile system, and it is this the instability of these band fluctuations that drives the dynamics that you saw there. Another way to think about this instability is that there is actually a characteristic length scale in the problem, which essentially arises by balancing active stresses against viscous stresses, or actually, not exactly. It balances by balancing active stresses against elastic stresses. You have to go back actually to the Q equation. And that length scale is simply determined by the square root of the stiffness divided by the magnitude of the contractility. The instability we saw yesterday in a field, essentially occurs when this length scale is of the order of the film thickness. And today we will see similar instabilities occurring in we see that the kind of turbulent dynamics that we see in the bulk system is also driven by instability that occur on this type of length scale. Are there any questions so far? Let's move forward. Okay, so this summarizes sort of something that I've already said, that we have these two length scales to keep in mind, and essentially when tau p is fast compared to tau a, the microstructure can relax very quickly and accommodate the injection of active stresses, and the system goes to a spatially homogeneous configuration. But when the relaxation of the microstructure is large compared to tau A, and the stresses are injected too quickly, the system cannot keep up, and then you see this kind of turbulence dynamics that I showed you before. So the first thing you can do is, with these equations, well, you can do a proper linear stability analysis, but beyond that, it's hard to do much analytically. So the next thing you can do with these hydrodynamic equations is integrate them numerically on a computer and see if you can reproduce, for some values of parameters, the same type of dynamics that they see in experiments. And that's one thing we did. So what I'm going to show you here is the result of this numerical integration in a box of size, L by L box, a square box with periodic boundary conditions. And I'm just going for now to show you two movies that are supposed to show you that the qualitative dynamics we get is the same as in the experiments. So this movie displays the order parameter. The color scale is the magnitude of S, the magnitude of the order parameter. Red is, let's call it S equal 1 in some, it's the maximum order, and blue is S equals 0, where the amount of order is 0. The lines are the direction of the director. So this movie will show the configuration of the order parameter. This movie shows the local velocity field. I actually don't remember, so actually we can look at the arrows. I think red is largest positive, and blue is largest negative, and green, no, it cannot be. Oh, no, sorry. The color, the arrows show the velocity field. The color shows the vorticity, the curl of the velocity. And I can't remember what is the sign, but say the red is positive vorticity, negative vorticity, blue is positive vorticity, and green is 0 vorticity. Okay? So vorticity tells you about whether the velocity field is making vortices, right? So positive vortices may be vortices turning clockwise, negative vortices turning counterclockwise, and 0 is the green in between. So let's look at these movies, and the idea is that you should see a dynamics sort of similar to the one we saw in the experiments. In addition, we have identified the location of the topological defects. The triangles are -1f defects, the dots are +1f defects. And what you see here is that the defects are, they may annihilate sometime, but then they're generated again. So unlike equilibrium, where a long time the defects will annihilate and disappear, here there is what we could call sort of like a steady state of the system, which has a non-zero mean number of topological defects, which are dynamically generated in the system as the result of the activity. The other thing to note, if you kind of have to pay little attention here, but is that the defects tend to be generated and move along the green regions, which are the boundaries between vortices in the velocity of opposite sign. And that's because these boundaries are the regions where band deformations of the order parameter are largest. So what you get the region of band deformation, and the band becomes very, very strong here, and that's in this region where the band is very strong, the defects are generated. The band also generates shear flows and generates these two vortices of opposite sign, and is along these walls between the order regions that the defects are generated and tend to move along these directions. Okay, showing you again the experimental image to point out that there is sort of a similar dynamics. Now another thing that you should notice in this movie, and maybe those of you who have worked with defects have noticed it already, is something actually a little strange. If you pay attention here, see these two arrows, the blue denotes the -1f defects and the red denotes the +1f defects. Remember I told you in equilibrium, plus and minus defects are like plus or minus charges, they always attract and then annihilate. But in this movie, the plus and minus defects, look at the arrows, are generated and then they move apart. They actually sort of, seems like they repel each other. And this is really strange, but I will show you in a minute that this is really the property of defects in active system and is one of the ingredients that allow you to reach these steady states with the non-zero number of defects on average. Okay? So before I do that, one more thing we did numerically. So this first of all is an image showing you sort of a close-up and a close-up of a snapshot of these dynamics, with the idea being that here you will have, this is flow, the color is vorticity, the arrows are velocity, this is a vortex going this way, this is a vortex going this way. This green region is the boundary between two vortices of opposite sign. It's also a region of high band deformation, and is where the opposite sign topological defects, the disclinations, appear in the system. We have also tracked the number of defects in the system as a function essentially of activity. This quantity here, it is actually known, I should have said that it is actually known that if you shear a nematic liquid crystal, if you shear it enough, you actually get defect generation in turbulence. Okay? And usually that kind of dynamics is characterized in terms of a quantity called the Eriksson number, which is essentially the ratio of shear stresses. Epsilon dot will be the rate, the shear rate. If is the shear viscosity, so it's the ratio of shear stresses to elastic stresses. Okay? So here we see a very similar behavior as a function of what we would call an active Eriksson number that we define by replacing shear stresses by active stresses. And we see that the number of defects grows with activity, but eventually levels out. And actually, extensile systems equal more defect than contractile systems, something we actually do not understand. We don't really have a good understanding of that. But again, this idea that you are getting this turbulent dynamics with defects generation in this active system, and you get the similar dynamics in shear nematic liquid crystals, it tells you that what's happening in this active system is that more and more we seem to find that we can get the very similar type of phenomena that are seen in equilibrium nematic when you apply external fields or external forces, but here we get them spontaneously. So we can actually make often an analogy between the two using these ideas. Okay, so here we solve the equation numerically, and we have some arbitrary parameters, so how useful is that? Maybe not very, but we've actually been able to do a little bit more to try to understand what's happening in the system. So first of all, again numerically, what we did is the following. We went back to our equation, and instead of starting either in a uniform or disorder state, it really doesn't matter, now we put in by hand a defect pair. So we put in by hand two defects. Here is the minus 1F defect, here is the plus 1F defect, and then we integrate the equation and see what happens. If we have no activity, what should happen? What should happen? This is a movie, I'm going to run it in a minute. What will happen? I have switched off activity in my equation, so what will happen here? They will attract, annihilate. Red is ordered state, so the system should turn pretty much red if I run it long enough. Okay? So let's see that indeed is what happens. It doesn't quite turn red here because I stopped it, but anyway, that's pretty much what happens. Okay? Now I do the same thing in a system with activity. And this movie is actually for a contractile system, so not like the experiment. That's our fault because that's what we did. But so this is actually a contractile system, okay? And something a little different is going to happen here. And I'm going to probably show you the movie a couple of times. So first, I'll just watch it. So what happened? First of all, let's just run it again. The defects still attracted, and actually attracted more. They moved faster. They annihilated faster. But then, the dynamics didn't end there. The deformations went the other direction, and more defects are generated, and again you get this kind of complex turbulent-like motion that seems to sustain itself. Okay. Now, if I had done the same thing with for an extensile system with alpha negative, I don't actually have a moving, but I hope I have. Oh, there it is. I have. Let's just look at this image here. So if I had done the same thing, but with for extensile defects, these are just snapshots. What I would have seen is that initially the defects, instead of moving towards each other, actually move away from each other. And actually, mainly is the plus 1f that moves away from the minus 1f, just like in the experiments. Okay? So let's see if we can understand that. I don't know why I had that later, but so it's actually not too difficult to understand that. If you think, often in equilibrium we think of defects as particles moving through the fluid with sort of an overdamped dynamics. But the defect is also a deformation of the director, and because of the coupling of defects to flow, the motion of the defect generates flow in a nematic liquid crystal. This is true also in equilibrium. It's called actually the backflow, because the flow generated by the defect affects the dynamics of the defect itself. Okay? This is usually pretty complicated because these couplings involve high terms that are fairly high order in the gradients of the order parameter. In this case, it's actually simpler. So let's look at the Navier-Stokes equation. In a very simple limit, Stokes limit, I'm going to throw away the time derivative. And let's ask, what is, so suppose I had a defect, either a plus 1f or a minus 1f, that creates this kind of deformation. And I'm going to ask what kind of flow, and I treat this as a source for flow. I can actually solve this equation and calculate the flow that my defect will generate, the flow field that will be generated by the defect. So I solve this equation using the configuration of one defect as the flow, and I get these black lines here. So what these images are, the red is the defect, plus 1f, minus 1f. The red lines are the flow profiles that I have calculated. You can actually calculate them analytically in this case, it's easy enough, that you calculate by solving this equation, putting in this configuration as a source. For the minus 1f defect, which has this symmetry, you find a very complicated flow field, but really all we care about is that the flow velocity vanishes by symmetry at the core of the defect, which you could eventually guess even without doing the calculation, as a matter of fact. For the minus 1f defect, again, complicated flow profile, but the flow velocity now does not vanish at the core of the defect, and in fact, the velocity at the core of the defect as magnitude, as strength proportional to alpha divided by eta, activity divided by shear viscosity. Okay? So not only is now zero, but the direction depends on the sign of alpha. For an extensile system where alpha is positive, the direction of the velocity generated by the defect itself at the core of the defect will point as that red arrow over there. That is, will point towards, so the defect looks like a comet, it will point towards the head of the comet. And for a contractile system, it actually points towards the tail of the comet. So if you really were to think of these defects as particles, Of course, there are then corrections coming from the passive backflow, so-called, but let's forget that. If you think of these defect as particles, you would say that a -1f defect behaves like, so when you think of them as particles, you say -1f and +1f attract each other with logarithmic interactions. This happens in equilibrium. In an active system, in addition, the +1f behaves like a self-propelled particle, and is propelled towards its head if it's an extensile system, towards its tail if it's a contractile system. Then you can go on and construct a little model of these defects as particles, and this is just in one dimension for this particular configuration of the defects. So again, if you neglected this backflow due to activity, you would say I have a +1f, -1f, I'm looking at the dynamics of them relative to each other. The dynamics is just controlled by balancing friction to forces due to the logarithmic attraction between the defects, and you could solve this equation and calculate the time it would take for these two defects to annihilate, which will depend on K and friction, okay? As well as their initial condition, how far apart they are initially. When you have the activity makes the +1f self-propelled. It makes these defects ride along with the flow, and the flow is the flow generated by the defect themselves. So you will modify this equation. You say that now there is the friction, the velocity of the defects relative to the background flow, so you have to subtract out this. If there was no interaction, the defect will ride along with the flow. And in addition, you put in the equilibrium interaction. So what we are doing here is modeling the defects as self-propelled particles with still the equilibrium interactions that actually come from elasticity, Nematic crystal. And for this velocity, we actually just put in that the velocity is non-zero at the core and proportional to activity divided by shear viscosity. And if you can actually solve this equation, and what you will find is that for a contractile system, the annihilation time will be shortened. And for extensile system, depending on the value of activity, they might still move towards each other and annihilate if a low activity. But if the activity is too large, they will actually move away from each other, just like we saw in the experiment. So you could start, of course, this tells you nothing about how the defects are actually created and annihilated. This just provides you with perhaps a simple way for trying to describe the dynamics. But there is a very important question that is still open, is how exactly does activity lead to defect generation? This tells you nothing about that. But at least this provides you a simple model that you may actually use to describe the dynamics, and I want to show you that it can actually be useful in a minute. But just to make clear that, because I told you that extensile defects sort of repel, while contractile defects attract you to activity, but I should stress that was for the particular configuration I showed you before, because it really depends on the relative orientation. So for instance, if I have an extensile system, and I have a -1f and a +1f oriented this way, well then the -1f will move away because it moves towards its head. But if they are oriented this way, then actually the -1f, they will attract. I don't think attraction is the right word, but they will move towards each other. And conversely, for contractile systems, if they are oriented this way, they move towards each other, but if they switch them around, they will move away from each other. So activity essentially drives the +1f defect to move faster than it would in an equilibrium system. And the directional motion of the -1f, the +1f defect is controlled by whether the system is contractile or extensile. So this actually, it's very nice it gives you a very nice way. So looking at this tells you that looking at defects can be a very nice way for identifying some fundamental properties of these active systems, which are not necessarily so obvious a priori. Because as in equilibrium, topological defects are fingerprint of the symmetry. You look at the defects, you might be able to tell whether the system is nematic versus polar. In addition, you look at the direction of motion of the +1 active defect. Is it moving towards its head? Is this comet-like defect moving towards its head or moving towards its tail? That will tell you whether this system is extensile or contractile. Now, if you are thinking about cells grab on substrates, they always pull in. It's obvious to everybody that has ever dealt with cells, the cells are a contractile system. But you look at vibrated granular rods, well, is that a contractile or an extensile system? We really don't know. Well, it's an extensile system because defects actually move, +1 F defects move towards their head as they're supposed to in an extensile system. So again, the lesson the message I'm trying to give here is that looking at defects can be a very interesting way of characterizing these kind of systems. Of course, there's a lot more to be understood. But are there any questions about this so far? Okay. So I want to spend the last 10 minutes telling you about how we've actually used these ideas of describing defects of self-propelled particles to describe the dynamics of defects in a confined system. So these are experiments. The Nematic or vacuum bundles that I showed you before were experiments done in the levels von Mirdajik at Brandeis University. Then Dajik got together with a group of Andreas Bausch in Munich, who is an expert in making vesicles. And they put their active nematic or microtubule bundles inside a vesicle. And when you do that, because of depletion forces, this active nematic actually goes to the surface of the vesicle. And so what you actually have is a two-dimensional active nematic on the surface of a sphere. Okay? So this is an image of a two-dimensional active nematic on the surface of a sphere. And although, again, these movies don't come out very well, but what you can see when you look at them, you should be able to see structures that look like +1 F defects and are now moving around on the surface of the sphere. Not surprising that with +1 F defects there, because we know, again, this is true in equilibrium, that if we put a nematic liquid crystal on the surface of a sphere, Martin is the expert at this, but nematic liquid crystal on the surface of a sphere, you cannot accommodate nematic order without some defects. You cannot comb air on the sphere, you're going to have some defects, right? And that's because the sphere, unlike a plane, which has net topological charge 0, a sphere has net topological charge 2. I think you had some lectures on defects perhaps last week. And so, if we try to put nematic order on the surface of a sphere, you have to have enough defects so that the topological charge will add up to +2. One way is 2 + 1 defects at the poles. Another way is 4 + 1 F defects at the corner of a tetrahedron, and that's kind of the structure of a baseball. Many of you are not from the United States, nor am I, but still, you might have seen a baseball. And if you think about the structure, see, this is 1 + 1 F. This is a baseball that has been decorated by drawing a director on it. They don't usually have directors drawn on it.
Except on the seat.
Except on the seat, they do have it on the seat, right? So this is a +1 F defect, right? You see it here. There is one here. There is one on the other side opposite to this one, and there is one down below opposite to this one. So there are 4, and these 4 are actually, if you put a tetrahedron inside the ball, these 4 turn out to be located at the corner of a tetrahedron. And you can actually show that that's the configuration of defects that makes the lowest energy in equilibrium.
maybe for the movie, you went back to the high resolution.
I don't know, these movies are not very good, but
Probably wasn't.
he wants to try to play with my computer, so we probably will lose all images, but that's we will see. Meanwhile, I'll try to tell you. So, but in this, so they have this active nematic on the surface of a sphere, and of course what they see is that they see 4+1F defects, but now the 4+1F defects, instead of being at the corner of a tetrahedron, are doing a couple of things. First of all, they're moving around all the time, but they actually change between two configurations. They are at the corner of a tetrahedron, then they switch to a planar configuration where they are all on the equator, and then they go to a tetrahedron with a point in the other direction. And they keep oscillating regularly between these configurations at a very regular frequency that they can actually measure. Did you succeed? No. And they actually can measure these, they track the defects. Okay, now here you have dots, so the dots can track the defects for you. They track the defects, they measure this frequency at which the configuration oscillates between a tetrahedral configuration, which is this blue line you can characterize in terms of the angle of the defects relative to each other. So the blue line corresponds to tetrahedral configuration, the red line corresponds to a planar configuration where they're all on the equator, and they oscillate at some regular frequency. And this frequency is measured for this particular value of ATP consumption is about 12 millivolts. So what we did is to say, okay, can we describe this by thinking of these defects as self-propelled particles on the surface of a sphere? And so it turns out you can. Now, I only have +1F defects, and you could also ask, well, why are defects generated in this case? And we think the answer is that these vesicles are too small for defects to be generated. If you had a bigger one, then you would get proliferation like you see in the planar system. And we can talk more about that. But here you only see 4 defects. The 4+1F defects, so they look like that. So we describe them as particles, their position, but they're self-propelled particles. And in fact, they are anisotropic objects. So we describe them by their position and the unit vector pointing towards the tail. So their dynamics will be over then dynamics of a self-propelled particle with a speed v naught, which is determined by the activity divided by the shear viscosity, and an interaction for which we take just equilibrium repulsive interaction in this case because they're all the same sign, logarithmic repulsive interaction. But we also need an equation for the angular degree of freedom. 2+1F defects at some arbitrary angle will have some angular interaction as well. We'll experience a torque. So we need to calculate this torque. We actually looked quite hard at the literature to see if anybody had calculated the torque between 2+1F defects, and we couldn't find anything. So we decided to calculate it by using the following trick, and this is in the plane. We said, well, suppose you, because what we know is what is the interaction between any two defects as points, but we don't know the torque. So we said, well, suppose we take 4 defects, 2 dipoles, +1F, -1F, +1F, -1F. Taking this configuration, which you could imagine generating in equilibrium by applying some type of fields of boundary conditions, that allows us to define a direction for each one of these dipoles. Then we can write down the total energy of interaction among these 4 defects, which will of course depend on their positions, and therefore can be rewritten in terms of the position of the red ones and the directions of the dipole of defects themselves. And then we take these distances, d1 and d2 to infinity, and we find that to leading order, we get the energy of interactions among the 2+1F defects. Next order, we get an angular interaction that does not depend on this d at all. And we take, so an interaction that depends on the angles, and we use that to calculate the torque. Okay. So I can tell you more about that, but that's a bit of a, it's not a typical calculation, but it's messy. So we calculate this torque, and then we, now we have 4 equational motions for the 4 defects. We actually put them on the surface of a sphere, and we follow the dynamics of these defects on the surface of a sphere. And we find oscillations at some characteristic frequency that is essentially the, so the characteristic velocity is the activity divided by viscosity times the radius of the sphere, and the characteristic frequency will be this divided by the radius of the sphere, and so it's determined simply by activity divided by viscosity, and it should increase with activity, which is what happens in the experiments, although we haven't really been able to do a quantitative comparison yet. The oscillations are actually not symmetric, and the system spends more time in the tetrahedral configuration that goes to the planar and then comes off that very quickly. And we think that's because if you look at the energy landscape, this is really sort of a saddle point. The planar configuration is really a saddle point in the landscape, and then the system goes off the cliff, if you like. But this is kind of interesting to us because it shows that indeed you might be able to use this idea of describing defects as self-propelled particles for be able to say something about the dynamics of this system. The experimental system is very interesting actually because the other thing that one other thing the experimentals are doing is if you take, actually this hasn't really been done with the vesicle, but you can also put these, you can make emulsion droplets essentially of this nematic, and if you put them, if you put these active droplets, as they call them, on a substrate, where the droplet is this nematic with defect dynamics on its surface, the droplet itself becomes self-propelled. The droplet itself spontaneously moves on the substrate. And so they are trying to generate, so the idea of these experiments is to try to reproduce spontaneous motion in the simplest possible way, with a minimal number of ingredients. And these droplets do seem to be, for now they move very little, they move very slowly, but they move. And so, so that's an encouraging result. Now the other thing that happens with these droplets is the vesicles again, is that the behavior actually is very size dependent. So the case where you get the 4 defects on the surface, I think these droplets are like maybe 30, 40 micron in radius. And the microtubule bundles are typically maybe 15, 20 microns in length, and that's what you get. If you make smaller droplets, under 30 micron in radius, actually then the microtubule bundles deform the droplet in a complicated way, and they make it, so then you have to worry, to describe this, you have to worry about coupling of the active two-dimensional liquid crystal to the vesicle, and the deformation caused by this coupling. So it gets much more complicated. And there's a lot more stuff to be understood there. But I will stop here. I don't know your probably time, but I will stop here. Anyway, because I think we probably can get coffee, which is always good. But I just wanted to say, so I've been working for some time on these active systems, which I think in my mind are very interesting non-equilibrium systems. As I said, they have in common this idea that instead of driving the system with a field or with applying a shear or something like that, you draw, each particle is individually driven. And what is interesting about this system is that, so normally, say, we apply, say, forces at the boundary of the system, and so energy cascades or flows from the large scale to the small scale, and then perhaps some collective behavior takes place. Here we are injecting energy at the small scale, and it's actually flowing the other way. It's flowing to the large scale and generating some interesting collective behavior at the large scale. And we most of the time we don't really know how to describe these new kind of systems. We have to, we describe them mostly phenomenologically. There have been some examples where the equations have been derived from some semi-microscopic model, but there is a lot more to do and to understand. There is also, frankly, a lot more to do in really trying to be more quantitative. I have shown you a lot of pictures, and we are capable with these either continuum or more microscopic models to reproduce a lot of the qualitatively the dynamics we see in the system. But there is still a lot of work to be done in trying to actually reproduce it quantitatively. We have parameters in the theory. We often don't know how exactly to relate them to the parameters in the experiments, and that really is going to require a lot more thinking. So I'm going to stop here and maybe there will be some questions. Any questions?
Yes.
At the same time.
What is the time scale of this switching?
So this was 12 millihertz in the experiment for these ATP concentration. So, again, the activity is driven by the rate at which ATP is consumed in the system. They actually have a way for maintaining the ATP constant. They have to replenish it because it goes away. And what we call activity will be proportional to the rate at which ATP is consumed in the system. So that's a parameter that they can actually change in experiments, not too easily, but they can actually change. And they find that the frequency goes up, increases as with ATP concentration, which is again qualitatively in agreement with the theory. So in these experiments, it was the number was 12 millivolts.
You have the movie.
Which movie?
Numerical.
Yeah. Okay. Another movie. That's our solution. So these are the defects going around. This is the mean angle moving on the energy landscape. This is a tetrahedron. This is a planar configuration. And since the mean angle doesn't distinguish between the radon pointing up and the radon pointing down, this thing goes up and then back down the hill, but really should be going down the hill on the other side, which would be the other tetrahedron. And that's not the movie, right? That's the so-called stereographic projection, which is you project a sphere on a plane, and it shows how these defects are moving around in the stereographic projection. This is Luca John who made this movie, not me. We are kind of incompetent as far as this thing goes. Making things like that. Sorry.
I just wanted to ask maybe, so if you would use just a normal nematic, like passive nematic, and drive it in some, I don't know, microwave setup or something like this.
Say it again?
If you drive the passive nematic with external force, like in some micro component, and you will do, for example, some thermal quenching, local quenches with tweezers, for example, by generating defects. Would you expect that, okay, so you have like dynamical system which is already flowing and to insert the defects. Would you expect to observe kind of similar behavior? Or?
Maybe, I guess you might be observing, so it wouldn't be the equilibrium configuration, but if you manage to slow down enough the dynamics of the nematic by rotational friction was sufficiently large, I would say that I would expect on a range of time scale to be able to see something similar. That is true. Now, actually, it's also true that there's been certainly a lot of work on nematic confined to, Ivan Maluk has done a lot of work on that, I think. Maybe not so much, I think there were bulk nematic droplet, meaning where the nematic is everywhere inside, not on the surface, so the defects may be more complicated, but it should be a similar kind of behavior. So I think the answer is yes, provided you can slow down the dynamics enough, and things don't just go to the Yes.
I forget if you mentioned, but on the active vesicle, is the nematic an active like contractile?
So this is extensile because this is again this microtubule suspension of microtubule bundles which are extensile. Okay, and I think in this case, if it was contractile, you should see something similar. But I have to say that we don't really quite understand why. I showed a figure at some point with the mean number of defects, and there were many more defects in the extensile case than in the contractile case for the same value of PVD. We don't really understand why that is. And so it's why I'm a little hesitant to say that it should be the same for contractile.
Thank you very much.